Oh, hello, old friend. It's good to see you. Let's talk about this word, fascination. It describes an unquenchable urge, which compels our hearts to quest and be captivated. As long as there are elegant explanations to complicated phenomena, science will never lose its romance. Over the years, I've traveled the world, indulging in my fascination in physics. And now, I find that a new hunger has woken within me. A fiery need to share these great ideas with the people around me. And so, I have assembled a team of some of the greatest, most lucid, most creative minds I've encountered in my travels. And I call them my Titanium Physicists. You're listening to the Titanium Physicists podcast, and I'm Ben Tippett. And now, allez, physique! The most astounding thing about the universe is that we can understand it. Ancient astronomers noticed that the night sky was full of little points of light, which marched across the sky every night. Most of them retained their position relative to one another as they marched across the sky over the course of the year. Now, given how they moved, ancient Greeks thought that they were little bits of ethereal fire mounted on a great celestial sphere, which enclosed the Earth and rotated around it. Finally, an explanation for what these little bright things are. They're stars. So, when somebody asks you to tell them about a specific star, you can only really tell them three things right off the bat. Its position, its color, and how bright it is. So you can say, that's a very bright blue star, or that's a very dim red star. Now, the marvelous thing about 20th century is that astrophysicists figured out all about how stars work. I mean, even though we only really know two physical attributes about each star, we have millions of stars to look at. And it turns out that stars only really have three things going on. They've got a mass, and they have an age, and they have a chemical composition. And those three things determine entirely how they look to us. So they're actually pretty simple objects. Well, figuring out their secrets required the knowledge and techniques of literally every branch of physics, from thermodynamics and gravity to quantum mechanics and particle physics. But yeah, physicists today have a pretty clear picture of how stars work. It's amazing. I'm amazed. Now, stars are these monstrous engines of destruction. They turn the light, pure, and virginal gas from the Big Bang into heavier, useless, crummy elements. Speaking of matters of corruption, I'm reminded of the Pseudopod podcast, a horror short story podcast where similar things are regularly explored. The host of said podcast is Alasdair Stuart, the gentleman, blogger, and essayist. Each horror story is bookended with one of Alasdair's essays reminding us that the monsters are us. He's currently working on a shared world series, a 15,000-word fantasy novel written between three authors. The part he's currently working on is a steampunk version of the end of the Avengers Assemble. Now, he's currently also writing the 10th Doctor source book for the Doctor Who role-playing game. Welcome back to the show, Alasdair Stuart.
Thank you for having me. How are you doing?
Oh, I'm so great, Alasdair. For you today, I've assembled two of my most powerful titanium physicists. Arise, Dr. Vicky Scowcroft! Dr. Vicky got her PhD from Liverpool John Moores in the UK. She's currently a postdoc at Carnegie Observatories, where she works on the Carnegie Hubble program. She also has a knitting podcast called One Starry Knit, and we'll have a link to it on our website if you want to find it. Now arise, Dr. James Silvester. Dr. James got his doctorate from the Queen's University in Kingston, Ontario, where he studied stellar magnetism. Until recently, James was a manager at the Scottish Dark Sky Observatory and has a podcast called Astrarium, where he and David Warrington introduce us to astronomy. All right, everybody, let's talk about Beyonce. All right, Alasdair. So I mentioned before that stars are really simple objects, and you might have trouble believing me about that because they seem crazy, right? The universe is full of them, and they're huge. I mean, the Earth is a complicated enough thing, and it's tiny compared to these big monster stars. So how do we know that these stars are actually pretty simple? It's a strange argument to make. And the idea is that, well, okay, it's like I said before, each star that we look at has a color and a temperature. It doesn't really matter where we look in the sky. All stars kind of look, well, they don't look the same, but you're not going to look down in the southern hemisphere and see all green stars, and then in the northern hemisphere, you're only going to see yellow stars, right? I mean, the distribution of stars and their colors and stuff looks pretty uniform anywhere you look in the galaxies. So the important thing is you look at a star, and it's got a color, and it's got a brightness. Now, the color is the important thing here. Your stovetop, right? You turn on an element and it glows red, and that means that it's hot. But if it glowed blue or glowed white, you would know that it was even hotter, right? Mm-hmm. So there's a relationship between the temperature of an object and what color it glows. So right now, everything around us looks, I'm looking at a black telephone right now. It looks black. It's not glowing any particular color. But if I looked at it with like an infrared camera, I would see it glowing in the infrared. Any object that has a temperature will glow a certain color according to that temperature. So the deal is that each of these stars that we see in the sky has a color associated with it. Some of them are red color, like Betelgeuse is a red star. Some of them are white. The sun is a white star, right? And there are blue stars out there. And each of the different colors corresponds to a different surface temperature, right? So a red star, its surface is a lower temperature than our white star, and a blue star is a hotter temperature than our white sun. So the deal is that if you wanted to sort all these stars out, like I said, you know what a star's brightness is, and you know what temperature it has based on the color. And so you can sort it. In a sense, you can make a big diagram. You can draw two axes, make the vertical axes the brightness, and the horizontal axes the temperature or the color. And then you can just look at different stars and you can see where on the diagram they live. A bright red star will be in the upper right-hand side of this diagram. A dimmer blue star will be in the bottom left-hand corner of the diagram, and so on. Mm-hmm. So you might imagine if stars were really, really complicated objects, if there were a whole bunch of crazy things going on inside them, there was a lot of diverse processes. What you would imagine is, as you looked at all the different stars around you in the sky and put them on your diagram would be blanketed with stars, because there could be a star of each color and each brightness. But that's not really what happens when you do this population survey and you throw them down on a diagram. What you see is they organize themselves into fairly specific rows and lines. This is the telltale sign that what's happening on the inside of a star is actually a fairly simple process. Even though it's probably happening at a monstrous scale, it's crazy large, we're dealing with crazy amounts of energy, the physical processes inside the star aren't really all that complicated. Because if you did, you'd see a lot more diversity in this diagram. So these diagrams are called HR diagrams. HR stands for Hertzsprung-Russell. It's illustrative right now to talk about where the star populations look like on this diagram. So imagine that you have a placemat. Okay. You're going to eat dinner, and you've been given a lot of peas, and you don't like peas, so you're going to play with them. So imagine that you have a placemat in front of you. So the horizontal axis running along the edge of the table, that's going to be your red-blue axis. So to your left-hand side, that's the blue color. Things to the right-hand side, the farther to the right it gets, the more red color it gets.
Okay.
Now, vertically, the edge of your placemat closest to you is dim, and then the farther up the placemat you go, the brighter the star is going to correspond to. Okay?
Okay.
You're essentially going to look out in the night sky and put a P down every time you see a star of a specific color and a specific brightness. So what I want you to do is imagine that you have a spoon, and you're going to put the spoon diagonally from the red dim corner pointing at the bright blue corner. We call that the main sequence. So you take a handful of peas, and now you pack a whole bunch of peas around your that spoon. And then your mother comes in and you say, "Screw off, I'm an adult, I can do what I want." So these correspond to fairly young stars. They're in the first phase of their life. They're not teenagers yet. And the deal is, when a star is born, when it collapses in from dust, when it's burning hydrogen, as our sun is, what it will do is it will line up along this line. And it's really interesting because it means that, there's a clear relationship between the brightness and the temperature. In this case, the brighter it is at first, the bluer it will be. Okay, so that's the main sequence. That's where your spoon is. I want you to take your knife now, and I want you to lay your knife horizontally along the top of your diagram. So where your spoon ends horizontally.
Okay, I got it.
Okay, so now you're going to take another handful of peas, and you're going to pack it along those. Okay? These represent the giant stars. They're really, really, really big, and they can come in an assortment of colors. Really bright blue stars, supergiants, but then a lot of different stars, like our sun might one day, they enter a phase called the red giant phase, where right now they seem to be, normal size brightness, white color light. Eventually, our star's fuel will start burning a different thing, and it will puff up. It will get really big and bright. And so, the stuff on the right-hand side of your knife, the peas over there, that's kind of the red giant area.
Okay, I got it.
Now, there are two other little populations of stars you can see. There are the white dwarfs. Those live in the kind of blue, dim side of things. So just, take a handful of peas and put them kind of beneath your spoon, beneath that main sequence. So, to the left of it, somewhere, right?
Okay.
So there are some stars that are bluish colored, but they're also fairly dim. And now there's going to be a packet of stars kind of to the right. Are there any other ones, Vicky?
So you've got the giant branch.
Yeah.
It's coming off from the middle of the main sequence to the top right. And then the supergiant to the horizontal line at the top. So the sun will become a red giant. And then the supergiants are even bigger than that, even brighter than that.
Oh, so you're saying the red giants aren't at the end of the knife. They're under the knife.
They're under the knife. They're big, but brighter than the spoon.
They're to the right of the spoon, but under the knife.
Yes.
They're old, so they're getting plastic surgery.
Yeah.
They're old, so they're under the knife.
They're the fork.
Yeah.
If we put a fork, from the middle of the spoon, going up towards the end of the knife that is not attached to the spoon, then that would be where the red giant branch is.
So the deal is that any particular star will start off somewhere along the spoon, along the main sequence, and then it will evolve this HR, this Hertzsprung-Russell diagram, to a different point, to one of the other populations, depending on how big it started and how old it is.
I think it's worth pointing out that describing a star's life is a little bit just like describing a transatlantic flight. You have a lot of activity the first few parts of the journey, and then you have hours and hours and hours of nothing, and then you have a bit of excitement at the end. And this is almost what's happening in stars. You have very active, quick processes, generally speaking, that happen during its formation, and then the star spends a lot of its lifetime on the main sequence in a very sort of stable state where nothing really changes. And this is most of the star's life. And then at the end, suddenly something interesting happens, and this varies depending on the size of the star, and that's also a very short process. So the main sequence part of a star's life is the longest, in essence the most boring part, and it's what's happening before and after that's different. And as you say, it's what size it was in the first place that determines what form the exciting action takes.
Right.
So talking about evolution, depending on the mass of the star, so very low mass stars, so stars like the sun or smaller, it's worth pointing out, I don't think we've really mentioned this yet, our star, the sun, is a relatively small star. Actually, I think it's worth pointing out, that interesting and important for life, because the smaller stars live longer than the massive stars. The massive stars are really like the rock stars. They have very short lives and they die violently. Where our star, the sun, is actually very sort of calm. It has a very measured life, and this is good for us because if we were orbiting around a massive star, we wouldn't be here now. So that's sort of a sideline, but it kind of paints a picture that stars like the sun are roughly speaking in the middle of this main sequence, and they're relatively calm. So a star like the sun, it's later stages, you'll get what becomes a red giant. So in the case of the sun, probably in about 1 billion years, the sun will start this process of slowly expanding. In fact, the sun's life is probably going to be for another 4 billion years, but as early as 1 billion years from now, there'll be some moderate level of expansion. And then as it gets closer towards the end of its life, it really will puff up, and it will get so large, in fact, it would probably encompass the orbit of the Earth in size. So it goes from what it is now to this massive giant, which we call a red giant. So it puffs up really big for a time, and then when it gets really close to the end of its life, this massive inflated red balloon, if you want to think of it like that, will suddenly just disappear back down, and we'll end up with what's called a white dwarf, which is sort of a very small object indeed. So that's what happens to a sun-like star, roughly speaking. And then when we come to more massive stars, these processes get a bit more violent. So I don't know if Vicky wants to talk about the more massive stars a little bit.
Yeah, if you've got like something that's much bigger than the sun, then it's going to carry on up the main sequence, but it's going to do it much quicker. Like James was saying, it's going to evolve much quicker. But once it gets up the main sequence, everything's going to go faster. And it's going to burn all these elements, and it's going to burn more stuff, and everything's going to be more violent. And eventually, it's going to run out of stuff to burn. It's like it burns hydrogen and then burns helium, and then as it runs out of all these different elements to burn, it burns the next heavier thing. But eventually you get to iron, and you can't do anything with that. That's the heaviest thing it can do. So it has to stop. And then there's nothing left to do. And there's nothing to hold up the star anymore. Before you had all this pressure from the star burning things to hold up the star and all the energy that was being pushed out was the thing that was holding up the star, and then that basically just switches off. So now the star will just collapse in on itself. So you've got this huge, massive star, and now all this stuff that was being held up is now collapsing in onto the centre of the star. Once that collapses in, it causes this massive shockwave, which then blows off all this material, and that's a supernova. And then there's this giant explosion, and that's it. So if you're a big star, you're going to explode, which is kind of sad.
Let's take it back a little bit. So the main idea here is that depending on what its mass is, a star is going to evolve in a slightly different way. And there are two things at play. The first thing is, the heavier the star is, the faster it's going to burn through its fuel and live its life, right?
Okay.
So imagine your Hertzsprung-Russell diagram again. So your placemat, you've got a diagonal spoon covered in peas, and then up above it you've got a knife covered in peas, the supergiants, and then you've got a pocket of peas over here, the red giant stars, and then a couple other pockets, dead stars stuff, okay? So the deal is, imagine that you have a population of stars that all formed at the same time. What those are going to look like is they're going to look like a distribution of peas along the knife and along the spoon. And then starting from the very tip of the knife, the stars are going to burn out all of their hydrogen fuel and start the next phase of their life. Moral of the story is, they're going to strip away from the main sequence in the supergiant and move into the red giant phase along the spoon. So starting at the top left-hand corner, you're going to take some peas off, and as time goes on, you're going to take the peas and move them from the spoon over into the red giant pile. And then slowly you see all of the stars stripping away from the main sequence as time goes on. And the moral of the story here is, you can look to see, say, at a globular cluster, a population of a couple thousand stars that formed around the same time, and you can figure out how old that population of stars is by making one of these diagrams and looking to see at what point along the spoon these peas are being stripped off. Because the farther down along the spoon you go, the older the group of stars must be. It's pretty clever.
Wow.
Yeah.
That's really cool.
I know, right? And so you can say, hey, how old is that population of stars? And you can be like, well, there's this many rock stars and they're in old folks' homes. You can look at essentially how many have burnt out at a certain time, and that tells you how old the population is. So HR diagrams are wonderful because on the one hand, they reassure us that stars are fairly simple objects, and there's kind of a life cycle to the stars. And then the other thing they tell us is they kind of inform us about the different properties it tells you how things change depend on mass. And so they allow us to come up with a pretty good picture of what's happening inside the star. And that itself is an amazing story. It's the story of attempting to hold back gravity. So let's talk about exactly what happens in the life cycle of a specific star. Imagine you have a star, maybe a little bit heavier than the sun. The sun is a little bit light. Well, it's pretty light. In fact, it's glowing all the time. That was a pun.
Yes.
Usually when we talk about stars, we talk about their masses in terms of how many times the mass of the sun is. So, for instance, if a star is less than 10% the mass of the sun, it won't be able to glow, essentially. It will just kind of collapse into a big brown Jupiter-y thing and float around in the heavens forever. Okay, so the deal is, imagine you have a great big cloud of gas, cloud of hydrogen, there's some helium mixed in, but a big cloud of gas in space. There's nothing around it. What'll happen is the gas has a little bit of temperature, And so the temperature causes kind of a pressure inside it because the gas is made out of little atoms. Temperature is just a reflection of how fast the atoms are moving inside of it. So if they're all kind of bouncing around at a certain thing, they won't collapse down into something. It's kind of like if you want to have a party and too many people have their own ideas, you can't get them to settle down to go to Chuck E. Cheese's, right? But if the cloud is large enough or if the temperature is low enough, what'll happen is the fingers of gravity will start to take effect and the cloud will start collapsing down under its own weight around some central point. The question we always have to ask ourselves when we're talking about star evolution is, what's keeping the gas from falling into the center? And at first, the answer is nothing. There's a little bit of thermal pressure, but usually in these cases where it collapses down, the thermal pressure is insufficient to keep it puffed up. So it starts to collapse down under its own weight. It takes a while. Collapse, and then it makes a ball of gas. And then the question is, okay, what keeps that from collapsing down any further? And the short answer is temperature does an okay job at first, but space is very dark and it's very cold. And I mentioned before that anything with temperature is glowing. And so anything with temperature is radiating photons. It's radiating energy out into space. So over time, the ball of gas becomes less energetic and it collapses more and more and more and more and more.
Okay.
Now, there is a thing from quantum mechanics. Have you ever heard of the Pauli exclusion principle?
I have not.
Oh, the Pauli exclusion principle says that two quantum mechanical objects can't be identical. And so by identical, we mean live around the same place, having the same momentum, having the same mass and the same particle type, having the same spin. There's a bunch of numbers we use to qualify particle, and this rule says that each electron has to have its own set of numbers. And the deal is that as your cloud of gas gets smaller and smaller and smaller, if the gas isn't hot enough, or if it doesn't have any energy, if it doesn't start burning hydrogen, what's going to happen is it's going to pack down so small that the repulsion of electrons from one another, quantum mechanically, is going to hold this thing aloft. And so as the gas collapses, it can't collapse down to a point because eventually this quantum mechanical effect kicks in and it will just hold it aloft. And so you'll end up with a cold ball sitting out in space.
Does it have a specific internal structure or is it just a sphere below which it cannot get any smaller?
Yeah, it is kind of a sphere below which it can't get any smaller. It doesn't have a structure like a crystal, exactly. Like, it doesn't have like a lattice structure, but quantum mechanically, it has a structure. It's called electron degeneracy. Essentially, it's kind of like desks in a classroom. Each electron sits at each different quantum number, and so all of the quantum numbers up to a certain point are filled up. So there is some structure there, but it's not like it's a diamond.
Got it.
And if the cloud of gas isn't mass enough, this will be the end state. And equivalent structures are the end state of a bunch of different stars if they're not heavy enough to burn all the different possible things. So this is essentially the default. If it's not heavy enough, it just becomes a ball sitting in space, not doing anything. But if the thing's heavy enough, something fantastic happens, because if it's heavy enough, then as it shrinks down, the pressure in the middle gets higher and higher, fast enough that the temperature in the middle will reach 10 million degrees Kelvin, and that's hot enough for hydrogen gas to fuse. There's a little bit of trivia on this. Hydrogen gas, you know what a hydrogen atom is, right?
Oh, yeah.
At these temperatures, the hydrogen electrons have slipped off, so they're just like protons flying around. The deal is, there's two positive charges. Positive charges repel. It takes a crazy amount of energy to get these protons to stick together because of this static electric repulsion. But this quantum mechanical effect called quantum tunneling kicks in, where the laws of nature say, essentially, they're a little bit leaky. They say, well, if the particles are moving fast enough, but not quite fast enough to make these things merge, quantum mechanics says that some of them will merge. So anyway, the moral of the story is they stick together and they merge into helium. The process is a little bit messy, but you start out with hydrogen and you end up with helium-4, which is 2 protons, 2 neutrons. And the deal is that there's a lot of energy that you can get from fusion. I mean, there's way more energy in fusing 2 hydrogen atoms together than, say, splitting a uranium atom. But the problem is that you need ridiculously high temperatures for this to happen. So in the center of the sun, what happens? You have this big cloud of gas. It's been collapsing. The center gets hot enough for 2 hydrogen atoms to fuse, and they do, and they release energy. They release a photon. And that photon says, oh, I want to go out to space where it's cold and dark. I hate it here where it's all cramped. And so it bounces its way out to the surface, And then this pressure of all these migrating photons as they move from the center of the star out into space are essentially what holds the hydrogen atoms aloft. And it's what keeps our sun from collapsing down into itself.
One thing that hasn't been mentioned is that the different types of stars have different structures. So stars smaller than the sun, actually very small stars, are completely convective. So that means that if you were to travel through the star from the surface to the core, throughout it basically almost be analogous to a boiling pot of water throughout every single layer. But as you get to bigger stars, you only have convection in the core, and then most of the stars is what's called radiative. So it's almost like you go from this boiling water scenario to suddenly just, photons streaming and radiating through. And then some stars have what's called a convective core with a bit of radiative envelope, so the bit between the core and the surface, and then they have a little bit of convection on the surface. And in fact, that's what's happening in the sun. It's not completely convective. It has a convective core, a radiative envelope, and then a bit of convection in the surface layers, what we call the photosphere. And that's why when you see pictures of the sun, it has this sort of almost like it's a very orangey, it looks like bubbled water. If you see these high resolution pictures of the sun, it almost looks like a boiling pot of water, but it's red orangey liquid opposed to transparent. So that means that you get different chemical signatures from different stars. So a star like the sun, all the elements that are made in the center of the sun, over time they present themselves on the surface, and you get this mix. You get almost a homogeneous mix of iron and other elements. But some stars, slightly larger mass stars, so stars are about 2 or 3 times the mass of the sun, because there's no convection in the upper layers, you don't get this mixing effect. You actually get accumulation of certain elements into almost clouds. So you go from a situation with some stars where it's completely mixed and homogeneous to other stars we actually see clouds of iron, clouds of silicon. So this gives sort of an indication of the different processes that are happening in the various layers of these stars.
What impact does that have on stellar weather?
Stellar weather. Well, that's a good question. I mean, you mean sort of in terms of like aurora and things like that? Yeah. Well, the stellar weather is really more to do with the magnetic field, and that's a completely different story. But the magnetic fields do play an important role in stars. But actually, it has some effects in the sun because you've got this convection going on. Any magnetic fields that come out of the surface, because they're almost in this boiling water situation, the magnetic field lines get twisted around. And an analogy of this is if you can imagine taking an elastic band and holding it at the two ends, and then you start twisting the ends. After time, you're going to get the elastic band winding up, and eventually it will snap. And this is what's happening in the sun, because these field lines are coming out of the surface, but because of the convection, they're sort of almost being dragged, moved to some extent, or at least there is some kind of effect happening there, and then eventually this can fling off into space. The thing is, the weather is related to the magnetic field, and the convection and the magnetic field sort of have a chicken and an egg scenario. In some stars where you don't have much of this convection in the atmosphere, the sort of magnetic field dominates and it helps freeze everything into these spots, whereas in the sun it's a different situation. And I should say that the chemical spots you see in more massive stars are different to sunspots. Sunspots relate to an area of cooler temperature in the surface, which is different from a chemical spot, which is basically a cloud of a given chemical element.
Got it. Thank you.
The convection is actually related to a fantastic piece of trivia. And it's more complicated. Stars, you have to deal with stars' convection. And integrating convection into it answers a lot of questions. And so it's really important. But if you imagine a star as just like this homogeneous ball of puffy gas where fusion is happening in the middle, and then you say, okay, imagine that a photon gets released in the middle. The star is a big soup of protons and electrons, and all of them have electric charges. And electric charges, they really strongly interact with photons. And so this photon is going to, every time it encounters an electron or a proton, it's going to get kicked in a different direction. And so it's going to kind of move randomly. It can't make a straight line out of the sun. And so it bounces a little bit here and it bounces a little bit there and back and forth. And over time, it eventually migrates and, statistically speaking, ends up out of the sun. And then it's like, phew, I can move out into space, hooray. But the amount of time it takes to do that is ridiculous. For our sun, 50,000 years. The plasma is so opaque that it takes 50,000 years for a photon to make it from the inside of the sun out into space. Even though, it's not like a light minute wide, the sun. But, kicks the light around and does it forever. So what happens in these stars is you essentially get it's millions of degrees inside and only thousands of degrees on the outside. And so essentially what happens is the water in the pod example, if you heat water too quickly, you get this gradient, this steep gradient of temperatures where it's really hot on the bottom of the water, really cold on the top. And instead of saying, well, the temperature, these photons are just going to bounce, all the photons say, screw it, we're taking an elevator up. And they make a glob of really hot plasma that then rises through the sun. But it's super tricky because so a magnetic field is generated when you have a charge that spins, right? Mm-hmm. So like an electromagnet's generated by taking a coil of wire and passing a current through it. So there's a relationship between magnetic fields and circulating electric charges. And because the sun is a plasma, because it's made of a whole bunch of charged particles, it's a fluid that interacts with the magnetic field because these little electrons can go wherever they want. And so they can spin and they hold on to magnetic fields. And so if you have one of these, there's a magnetic field passing through an electron down, and then the electron decides to take one of these convective elevators up, it's essentially grabbing the magnetic field and it pulls it up and it twists it because of the rotation of the sun and stuff. And so you end up with this big tangled up magnetic field inside the sun. It's one of the harder fields of physics.
Wow.
Yeah. And you get that thing that James was talking about where, essentially a sunspot is what happens when these magnetic fields get so twisted around themselves that where an elastic band would break, the magnetic field pinches off into a smaller little loop. And then that loop buoys up to the surface like a bubble or piece of string. And as it exits the sun, the loop is always crossing the surface of the sun at two spots. And those are those sunspots. And then as the magnetic field leaves the sun, it creates one of these coronal mass ejections following the magnetic field.
I didn't know that. I had no idea that sunspots were a surface extrusion of an internal structure.
I know, right?
That blows my mind.
So one last bit of thing inside the sun, the fusion that's happening, it's happening at a fairly low rate. There's quick side. One question is, hey, we know that particle colliders, like we have the capacity to make bits of gas that are as hot as the center of the sun. Why can't we fuse hydrogen together and essentially repeat what's going on inside the sun and harness it to make awesome fusion generators and clean energy forever, right?
Uh-huh.
And the deal is that I mentioned before that you need this quantum tunneling effect inside the sun. This temperature inside the sun isn't hot enough for the particles to formally merge. They have to rely on this subtle quantum mechanical effect to happen. So the deal is that you need a much, 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 much hotter temperature to get reaction rates that would be useful inside of a laboratory or inside of a power generator. So inside the sun, this fusion is happening, but at a fairly low rate. But the deal with the sun is it's huge. So even though it's happening at a fairly low rate, it is generating enough energy that on the bulk, it's causing this. But there's another much crazier piece of trivia. It was called the solar neutrino problem. Have you ever heard of this?
I have not.
Okay. So, Homestake Mine, the Homestake experiment, I think it's called. So every time these hydrogen atoms fuse, they generate a neutrino. A neutrino is it's a subnuclear particle. It's a tiny little particle. It's barely got a mass. It's traveling almost at the speed of light because it's so light, and it barely interacts with anything. It interacts only through the weak nuclear force, which is tiny, as the name suggests. And so what happens is these neutrinos generated inside the middle of the sun, they don't bounce off anything because they're so weakly interacting. So anytime two hydrogens fuse, makes a neutrino, that neutrino beelines it for outer space. And we can measure these neutrinos. The measurements have to be really subtle. Measuring the neutrinos is it would give you a real-time sense of how fast fusion is happening inside the middle of the sun. Now, here's the crazy bit. They measured it in a mine in the United States. And the answer was 1/3 the neutrino rate that they expected.
Really?
Yeah. And they didn't know why. And they thought that maybe one possible explanation was that fusion had stopped in the middle of the sun and the sun was going out, but we hadn't received the news yet, right? 50,000 years for a photon to emerge from the sun,
Of course.
So they thought maybe the sun had gone out, but we just hadn't gotten the news yet. Of course, the real answer is subtle. The sun hasn't gone out. The deal is that neutrinos, it turns out, in a Canadian experiment at Queen's University, in a mine in Sudbury, Ontario, Canada, they discovered that neutrinos change their type. So we were looking for neutrinos of one type, but there are two other types it could be. And as the neutrino marches from the inside of the sun out to our detectors, it mixes itself up and changes into different types of neutrinos. And so the deal is the reason we only saw a third of the reaction rate was because 2/3 of the neutrinos had turned into other types that we couldn't detect.
So the good news is the world isn't ending, and the bad news is that neutrinos are card sharks, basically.
Yeah, that's right.
Cool. Okay.
Yeah. Okay. So that's, crazy business. We thought the sun's going out. It's not. Vicky, it's your turn.
Okay, so we were talking about fusion, right? So once you've started the process where you've got your hydrogen fusing, you've got the quantum tunneling going on. It's like, yeah, I could fuse. I'm all good. So that process releases some energy. So now you can make helium, which is the two protons and the two neutrons, and that's making energy. But eventually you're going to run out of hydrogen. Your main sequence is all the time that it's fusing hydrogen into helium, and that takes 10 billion years, for a regular star like the sun or something. So that's forever. But then once you've run out of hydrogen, that's when the interesting stuff starts to happen. Now you've got to start burning heavier stuff like helium. So at this point, you've got all this helium that you can burn. One of the first things that it can do is something called the triple alpha process, where you've got 3 helium atoms and you want to shove them together to make something else. So you start basically doing the same thing as you were doing with the hydrogen, where you're forcing them together to just shoving them all together to with your quantum tunneling and to make the helium. But now you're doing with the helium atoms to make heavier things like carbon. And this is going to make you things like carbon and then nitrogen and oxygen by just shoving more and more helium atoms on top of each other. But there's 2 ways this can go. Big stars, you can do this. It's going to be hot enough that you can do this. You can fuse your helium together. Eventually you'll get heavier elements and you'll keep shoving them together and you'll burn all of these. But I think the cool thing, is actually in the smaller stars, where it's not hot enough to do that. So you've got all this helium, and then eventually your hydrogen runs out, blah, blah, blah. But your helium isn't hot enough to start fusing your helium together. So once you've run out of hydrogen, your star starts to collapse back in on itself a little bit. And what that does is increases the pressure on all the helium that's in the core of your star. And eventually the pressure will get so big on the helium that it will crush all the helium atoms together so much that you're getting the exclusion principle coming back into play again, exactly the same as Ben was talking about before, but now with helium. What that does is eventually it just sets all the helium on fire, and that's called the helium flash, and that just blows the helium up, all of it together. Yeah, it's super quick. It's a few seconds, and in star terms that's ridiculous. Everything else in star terms happens on years, and this is happening in a few seconds. You don't even see it, but if you look at the HR diagram, you can see that these stars have shifted in the HR diagram because of the helium caught on fire, and that only happens in small stars. So I think that's cool.
That's very cool.
One notable thing is the deal with these larger stars is that there's always a little bit more energy you can get by combining 2 elements into a heavier element until you reach iron. So you smush some helium together to make a carbon. You don't get as much out of it as you did with hydrogen, but it's happening a lot faster. The reaction rates are happening faster because, smushing 2 hydrogen atoms takes a long time. You need to rely on this weird quantum mechanical thing. So even though you don't get as much energy per reaction, the reaction rates are happening a lot faster. And so in a helium burning star, it will release a whole bunch of energy, much more energy, say, per second than a normal hydrogen burning star. And this will cause the star to change. What'll happen is suddenly the photons moving out from the center, there'll be a lot more energetic ones, and they'll puff out the star. They'll push the gas out to a much wider size. James mentioned it earlier. Our sun will probably end up eating the Earth. We call those red giants. Like we mentioned, there's a pocket of red giants on the HR diagram. And that's kind of the destiny of a lot of these heavier stars. They'll burn helium and they'll puff up and they get really, really, really big and bright, but red colored because they're not hot, but they're puffy, I guess. Moral of the story is they get big and they get red. And then they burn out of helium. And so they start smushing together. And then so the core collapses, the pressure increases, and the story keeps going on. If the star is massive enough, it will end up burning, smushing together heavier elements, until all that's left in the middle of one of these stars is iron. And you can't do anything with iron. It takes more energy to smush something into iron than gets released. Iron is the tipping point. So, uranium is much heavier than iron. And that's why if you split a uranium atom, it releases energy. So for atoms lighter than iron, if you smush them together, you release energy. You get it?
I get it.
Okay, so question is, where did all the stuff on Earth that isn't made of iron come from? You've heard Neil deGrasse Tyson and Carl Sagan talk about how we're all made of star stuff.
Mm-hmm.
So what happens is, we talked about supernovas before already, but essentially what happens is, if a star is sufficiently heavy, and if it's run out of other types of fuel, what'll happen is, as it collapses down on itself, starts to make a neutron star or a black hole. And that process releases a ton of energy all of a sudden. And so you end up with a shock wave of energy moving out from the center. There's a ton of neutrinos, ton of photons, ton of everything. Just a shock wave of pressure moving out from the center that blows off the envelope of the star, which is what you see. That's the supernova, right? It gets really, really bright all of a sudden. But in that moment, the pressure is so high in that shock wave that's when these elements fuse into heavier things like uranium and metals heavier than iron. So everything on Earth that isn't hydrogen or helium came from the inside of a star that went supernova a long, long time ago. But additionally, any element that's heavier than iron came about as a result of the shockwave from the supernova.
I did not know that.
So, it's all made at the very last second. It's like an undergraduate student who, does all their work the day before. It's all
but only undergraduates do that.
Yeah.
Not grown-ups like us.
Of course not. There are a couple of things which I just want to make sure I've got clear in my mind. There is a correlation between size and colour. Am I right?
Sort of.
There's a correlation between temperature and colour, and that kind of relates to size, because if you have a given temperature to sort of balance, you're going to be a different size. So to put it another way, you don't have two stars that are the same size, roughly speaking, and completely different temperatures, within reason, if we're talking about main sequence stars, for example.
Got it. Okay, that's really useful. Let's talk briefly about binary and multiple star systems. What impact does having a partner or multiple partners have on the internal layout of a star?
That can have quite a fundamental effect on the internal layout of the star. Particularly, in a binary system, you can have a situation where one thing that happens is you can have mass transfer. So that means material from one star goes to the other. So basically, if you have one star that's slightly larger, it could, in a sense, feed off the other star.
I've seen diagrams of this, yeah.
Also, other things happen, like, for example, usually stars are in binary systems. If they start with different rotation rates, that means how fast they spin, within time they may actually synchronize. So being in a binary system causes the two stars to have similar rotation rates, which can have some sort of other effects on the star. So being in a binary system does have quite a few effects on the star.
So what's interesting is that most stars are actually in binary systems, or more.
Really?
Most stars form in clusters. Most of them are actually in binary systems. We're quite weird to not be in one. But not all of them are necessarily going to be in a system where they're so close that they're going to have a dramatic effect on each other. But when they do, it can be super dramatic. They could have mass transfer, or just one could completely engulf the other one.
Your point that most stars are in binaries, I find that really interesting, because when I was growing up, there's a show which I'm sure on the BBC over here called Horizon, which is I always referred to Horizon as science tapas. You would get kind of a 50-minute documentary about a thing, and one week it'd be trees, and the next week it'd be the space shuttle. And I was this kind of weird, slightly apocalypse-obsessed kid, which I think says a lot about why I've ended up working in horror. And I distinctly remember an episode of that which dealt with the nemesis theory, the idea that the sun has a dark twin. And at the time, I was 13, so at the time I was going, I'm dead. I'm dead at some point in the next 10 years. I might have sex by the time that happens. I'm going to have to be okay with that. And obviously, over time, that's been completely disproved multiple different ways. But the thing which I find really interesting is, now you mentioned this thing about how most stars are binaries. That puts the admittedly pretty wacky, because I think it was even referred to as the Death Star hypothesis at a couple of points. That puts the fundamentally pretty wacky nemesis hypothesis in a really interesting context. That there was actually pretty solid science behind it. It was just wrong, you know?
Yeah, it's just we probably would have known about it if we were in a binary system. The fact that it was like hiding, that
ninja
was
star.
Weird. Yeah, like a ninja star would have been weird.
Look, like I say, looking back, even age 13, I was going, yeah, maybe. Hopefully not.
But no, because stars tend to form in clusters. Like, it's not just like a cloud that collapses into one star. There'll be a cloud and it will form a few stars, and they might break off, and like you'll get a few single stars, but you would tend to get like a few stars together. So it's not rare for a star to be in a binary system.
Okay, so I've got some other fun trivia for you for these binary systems. You asked if they can alter each other's evolution. We mentioned accretion, right? So you can have two stars, and the deal is that somewhere in between them is going to be kind of a point at which the gravity from one star is stronger than the gravity from the other star. If you have a gas that moves across that point from one star, say the star like a red giant, then the other star will start accreting gas from the red giant. The cool bit is that we mentioned that lots of these processes depend on mass. So there's like a cutoff mass for a supernova to happen. And there's a cutoff mass for certain types of hydrogen burning to happen, or helium burning to happen. So the deal is you can get one star that's just on the cusp of, say, going supernova, but it's not quite heavy enough. And then the other star, big, it decides to puff up, start eating its helium, and then suddenly there's mass flowing from one star onto the other star. And the other star that didn't quite have enough mass to do the thing suddenly does. And it explodes. And that happens. Those are, type 1A?
Those are like standard candles. So, because we know the exact mass that happens at. We know how bright it looks to us. We know how bright it actually is. So we can tell how far away it is. So we know everything about that thing.
Because we know how bright they are. First off, they're huge bright. So you can see them from halfway across the universe. But because you know exactly how bright they're supposed to be, you can observe them. And you can tell how dim they are, or you know what color they're coming in at. You can use that to figure out how far away it is from us. And astronomers use these particular types of stars to piece together the universe's expansion rate. They used it to piece together the history of the universe's expansion, and from those, we know that the universe is accelerating in its expansion.
Yeah.
Really?
Crazy business.
Yeah. So it's not just getting bigger, it's getting faster and it's getting bigger.
Yeah, and these binaries, this binary accretion thing is the reason we know.
Wow.
Well, that was fun. Thank you, James. Thank you, Vicky. Your efforts have borne fruit, and that fruit is sweet. Here's some fruit. James, you get a kiwi fruit.
Oh, yum.
And Vicky, you get a jackfruit.
Yo.
I'd like to thank my guest, Alasdair Stuart. Thank you, Alasdair.
Thank you so much for having me on, guys. This has been brilliant.
That was super fun. All right. Okay, listen, TIE Fighters. There's 4 things you need to know. Firstly, leave us an iTunes review. Whenever I feel sad, I go to iTunes to look at new reviews because it cheers me up. So you better do it because your words, they're fueling me. Okay, second, there's a podcast app called Podiversity. It's on the Android phone. It's a subscription for content-based app, so it's not free like the other ones, but it's like Netflix, but for podcasts. And they pay us! The more you listen to the show, the more they pay us. So it's nice to get paid a little bit for our efforts. Thirdly, t-shirts. We do sell t-shirts and they're really nice. Chelsea Anderson from Calgary designed a lot of them and they're wonderful. Go to the TIE-Fi website and buy yourself a sweet shirt. They're really high quality. They last forever. Bethany's had one for about 3 years and wears it like every day. Hey, you guys, nice shirts. Fourthly, if you want to contact us, you can send us an email. My address is barn@titaniumphysics.com. BARN@titaniumphysics.com. I look forward to fan mail and I forward word. People are fan mail. So if you want to tell James how lovely his voice sounds, send me a note and I'll pass it on. Also, we're on Twitter and Tumblr and Facebook if you want to find us. Okay, so that's it for the main part of today's show. If you like listening to scientists talk about science in their own words, you might also want to listen to the other shows on the Bracculate Media Network. I'm going to rattle off the shows. There's Astrarium.
Yeah.
Yeah, it's about astronomy. There's Science Sort Of, which is about news and culture and stuff. Science, yeah, it's fun. Technically Speaking is about engineering, collapsed wave functions about chemistry, and there's So, you guys, we need a biology show. Get on that. The intro song for today's show is by Ted Leo and the Pharmacists, and the end song is by John Vanderslice. Until next time, my friends, good day, and remember to keep science in your hearts.
Angela, don't be mad. There's something I gotta tell you, dear, before you come back here. I lost your bunny. I let him out of the cage. He was eating spring mix on the carpet, jumped through a window out into the haze, hopped down Magnolia